Okay, so we're going over module 13, network virtualization. So there's lots of ways we can look at this, and it's kind of interesting that a lot of times virtualization and cloud are synonymous when kind of sort of they aren't. Let me see what's, I gotta move things around over here. There we go. Anyway, so we'll talk about network virtualization. We'll go over cloud computing, virtualization, virtual network infrastructure, and then we're going to get into some of the sticky like SDN stuff, which is a new level that we're putting on our networking, getting away from the CLI and moving more towards a an environment that we can easily automate, which is really nice. And then we'll talk about the controllers that are used in those things. Can you guys hear me okay?
Yeah, it's all kind of coming in clear.
Okay. Okay. Sorry, I was just checking chat. Okay, so we're going to talk about there's a video. Please watch it. Have you guys been watching the videos? They are pretty darn good. So please take a look at the video, cloud and virtualization. Kind of gives you a little bit of a reminder of, some of the things that are going on. We're going to do a cloud overview and why businesses use cloud resources. There's reduced costs. We've got rapid response. If we need to scale up, we can do that on the fly. So we've got 3 main cloud computing services, and we're using the NIST specification simply because if we have a strong definition by a standardization organization, that's what we should be sticking with, so that we don't end up in that gray area. So we've got software as a service, platform as a service, and infrastructure as a service. And cloud service providers have extended this model to also include IT support for each of the cloud computing services. So that's IT as a service. And for businesses, IT as a service can extend the capability of the network without requiring any investment in new infrastructure. They won't have to train new personnel, and they won't have to license new software. So that's a plus for business for sure. So we've got our public cloud, our private cloud, and hybrid clouds. So our public clouds, it's made available to the general population. We've got cloud-based applications and services that are made. For our private clouds, we've got stuff that's designed specifically for an organization. A hybrid cloud is a little bit of each. And community clouds. So if you're, for example, they give the example of HIPAA, which is a wonderful example because healthcare organizations have to comply with specific rules and laws and regulations regarding their PII. Personally, so their PII and some of their rules. So this allows an organization, a community, to set something up that's going to meet all of the specific requirements that they're going to need. So we've got a cloud computing versus data center. So we need our correct definitions for our data center and our cloud computing. So our data centers, of course, are physical facilities that provide the compute, network, and storage needs of the cloud computing services. So cloud service providers use data centers to hold their cloud services and cloud-based resources. Excuse me. And then we get into virtualization, which we should be quite familiar with. The term cloud computing and virtualization are often used interchangeably, but they mean different things. Virtualization is the foundation of cloud computing, of course. Without it, cloud computing currently implemented wouldn't be possible. So virtualization separates the operating system from the hardware, right, with that hardware abstraction layer. And we've got AWS and Azure and GCP and other providers that offer virtual cloud services that can dynamically provision servers as required. And these virtualized instances of servers are created on demand. So, and they are scalable. You know, when we were in our SQL Server class, we could have changed how much RAM was utilized. So you can scale things a lot easier in a virtualized environment. It's not the same, you know, adding RAM in a virtual machine is a lot easier than adding RAM to a running server, a hardware, right? Huge difference there. So we've got dedicated servers. So historically, this is how we've had things set up. We've had all of these, you know, dedicated servers. We'd have one for a web server, one for an email server for our Exchange, one for our SQL server, our file server. And the problem with that is when a component fails, the service that's provided by that server becomes unavailable. And that's our single point of failure, and we want to get rid of that. Dedicated servers were generally underused. Having one, you know, hardware server, you know, just for one thing was kind of silly. They would sit idle for long periods of time, waiting until there was a need to deliver whatever specific service they provided. So these servers wasted energy, took up more space that was warranted for the service that they were providing. And that's known as server sprawl. And so with virtualization, the use of virtualization normally is going to include redundancy to protect from a single point of failure. And it's really easy to manage redundancy in the cloud because you don't have to buy all new equipment, right? The hypervisor, of course, is a program, firmware or hardware that adds the abstraction layer on top of the physical hardware. And then that abstraction layer is used to create virtual machines that have access to all the hardware on the physical machines, such as the CPU, the memory, the disk controllers, and the network interface cards. So that hardware abstraction layer is is the workhorse. Of course, advantages of virtualization. There are so many. Less equipment is required, energy is consumed. We've got easier prototyping. We've got faster server provisioning. We've got increased server uptime, improved disaster recovery, and then we've got legacy support also. So if we have software that needs to be on an older system, we can do it through a VM. And here's our abstraction layers. As we can see, at each of these layers of abstraction, some type of programming code is used as an interface between the layer below and the layer above. And the hypervisor is installed between the firmware and the operating system. The hypervisor can support multiple instances of operating systems. In particular, in the server class where we had our VMware Workstation player hosting the Windows Server 2019 server that ended up being the Hyper-V host for our Windows Server 2016 VMs. That nested virtualization had a lot of moving parts when it came to the hypervisors. excuse me. So our type 2 hypervisors are also called hosted hypervisors. And the big advantage of type 2 hypervisors is that it's that managed console software is not required. We've got our virtual network infrastructure also. So with type 1 hypervisors, they're a bare metal approach. So that would be like your ESXi, or if you use Hyper-V server, which is not the same thing as a Hyper-V server role in Windows Server. So Hyper-V server in Windows is it's a standalone operating system. They have to offer it for free because it's based on Zen technology, which is open source. And so our type 1 hypervisors would be that, or would be ESXi for VMware. Our VMware workstation player and our Hyper-V server role would be type 2 hypervisors. You get that? So with type 1 hypervisor, the hypervisor is installed directly on the server networking hardware. And then instances of the operating system are installed on the hypervisor. And type 1 hypervisors have direct access to the hardware resources, so they're more efficient than hosted architectures because they don't have to manage a host operating system as well. Our type 1 hypervisors improve scalability, performance, and robustness. One of the reasons why we don't use Hyper-V server instead of our Windows Server 2019 Hyper-V server role is because the Hyper-V server operating system that Windows has doesn't have as a nice configurable console for us to play with. So our type 1 hypervisors include, add scalability and lots of great things. Installing a VM on a hypervisor. So we're going to have management software that's used to manage multiple servers using the same hypervisor. And the management console can automatically consolidate the servers and power on or off the servers as required. If a server component fails, then the management console is going to automatically move the VM to another server. Cisco's Unified Computing System Manager controls multiple servers and manages resources for thousands of VMs. Over allocation is when multiple operating system instances are installed, but their memory allocation exceeds the total amount of memory that the server has. So over allocation is a common practice because all 4 operating system instances rarely require all of their allocated resources at any one moment. So that's our dynamic memory. Things can get really complex. So VMs are movable and the network administrator has to be able to add or drop or change network resources and profiles to support their mobility. This process would be manual and time consuming with traditional network switches, right? That would be a lot of time spent in the server room running back and forth and plugging things in and stuff. So traffic differs from the traditional client server model. So traditionally, there's a considerable amount of traffic being exchanged between virtual servers, and that would be east-west traffic. So they're in between going to and from multiple servers. That changes in location and intensity over time. So north-south traffic is typically traffic that's destined for offsite locations like another data center, another cloud provider, or the internet. So if you had cloud services with Azure or with AWS, and you also had, so if you had a hybrid cloud model and you had stuff in AWS or Azure, and you also had your infrastructure on your prem, then your north-south traffic would be that traffic from your on-prem material to the cloud. or to the internet. So lots of complexity. So our existing network infrastructures can respond to changing requirements related to the management of traffic flows by using quality of service, right? And security level configurations for individual flows. But in large enterprises using multi-vendor equipment, each time a new VM is enabled, the necessary reconfiguration can be really time consuming. So each network device can be segmented into multiple virtual devices that operate as independent devices. Examples would include our sub interfaces, virtual interfaces, VLANs, and routing tables. And our virtualized routing is called virtual routing and forwarding. So that would be VRF. So anytime you see VRF, think virtual routing and forwarding. So software-defined networking. So this is where we are taking taking some of these network changes that happen sometimes when we're not looking, and creating management interfaces where we can set up triggers and scripts to automatically load balance and change things according to the network schema at the time. So there's a good video on SDN. Please take a good look at that. That's going to talk about some of the different open sourced protocols. It'll talk about the Open Network Foundation and OpenFlow and OpenStack. And then it's going to talk about some of the controllers that we could manage. So some of the things in software-defined networking is we are dividing the control plane and the data plane. The control plane is used to make forwarding decisions. The control plane contains layer 2 and layer 3 routing mechanisms, like routing protocol neighbor tables and topology tables, IPv4 and IPv6 routing tables, STP and the ARP table. Information sent to the control plane is processed by the CPU. The data plane, on the other hand, of each device is used to forward the traffic flows. So routers and switches use the information from the control plane to forward incoming traffic out of the appropriate egress interface. Information in the data plane is typically processed by a special data plane processor without the CPU even getting involved. And here's an example of the breakup of the control and data plane. So the control plane function is removed from each device, and it's performed by a centralized controller. And the centralized controller is going to communicate control plane functions to each device. And each device can now focus on forwarding data while other centralized controller manages the data flow, increased security, and provides other services. So it's separating the control plane and the data plane. Oops. Then we've got the management plane, and the management plane is how you have how you access and configure devices in your networking. So protocols like SNMP use the management plane. SSH, TFTP, FTP, all of those things. So when we're talking about software-defined networking, so it's network virtualization, and ACI is cloud integration of that. So some of the components of SDN, we've got the OpenFlow protocol, and that's a basic element in building SDN solutions. We've got OpenStack, which is often used with Cisco ACI. And orchestration in networking is the process of automating the provisioning of network components such as servers, storage, switches, routers, and applications. So to orchestrate all of these things, we would be using our virtualization technologies. So traditional and SDN architectures. So here in our traditional architecture, each device has its own control plane and its own data plane, right? In SDN architecture, as we said earlier, we're stripping the control plane off. It's turning that into the SDN controller. So we can manage all of those physical devices through one interface. Routing decisions and packet forwarding are the responsible of the device operating system. And in SDN, management of the control plane is moved to a centralized SDN controller. And we're just kind of comparing the two here. Some more comparison. So the complete SDN framework is shown here. Notice the use of application programming interfaces, APIs. It's a standardized definition for the proper way for an application to request services from another application. So the APIs come in to play and are extremely important integral parts of this. One API that we would use in networking in particular is Postman. So Postman is an application. We would use the REST API, and that would allow us to access the resources that we're trying to manage. The SDN controller uses northbound APIs to communicate with upstream applications, and that helps the administrator shape traffic and deploy services. The controller uses southbound APIs to define the behavior of the data planes on downstream switches and routers. And OpenFlow is a widely implemented southbound API. So you're going to be using your OpenFlow for your southbound to manage your routers and your switches. Actually, if we go back to this example, so Postman would be the application layer, northbound API, but it would be using REST API for southbound to manage your resources. And controllers. So we've got SDN controllers in operation. So each flow traveling through the network has to first get permission from the SDN controller, and that's going to verify that the communication is permissible according to whatever network policies that we have implemented. All the complex functions are performed by the controller, and it's going to populate the flow tables, and the switches are going to manage the flow tables. So within each switch, a series of tables is implemented in hardware or firmware. Boo.
I feel bad for Corey. He can't say anything.
Oh, he is saying something. Wait a second. Let's open chat. Cameo appearance. Yeah, very good. Okay. Let's see. Anyway, within each switch, there's a bunch of tables implemented in hardware or firmware that's used to manage the flow of packets through the switch. To the switch, a flow is a sequence of packets that matches a specific entry in the flow table. The three tables shown here, or shown in the previous, are shown here, are the flow table. And the flow table matches incoming packets to a particular flow and specifies the function that are to be performed to those packets. There may be multiple flow tables that operate in a pipeline fashion. There's a group table, and so the flow table may direct a flow to a group table, which may trigger a variety of actions that affect one or more flows. And then we have the meter table, and the meter table, that table triggers a variety of performance related actions on a flow according to the ability to rate limit the traffic. So our meter table would be like quality of service, kind of, sort of. So there's a video on Cisco ACI. Cisco developed the ACI to manage and the automation and integration of SDNs in more advanced and innovative ways than in other approaches, which is great because it really is much better for us as administrators to be able to utilize a one console dashboard for all of our devices, that we can see them all simultaneously and we can see the traffic flow in real time, as opposed to trying to jump from one into one router or switch at a time. Because we really, when we jump into a router or a switch in the management interface, we really don't have an opportunity to see, you know, what's going on and what effect it's having as readily as we can from a dashboard. Okay, so that said, do we really need to know the Cisco CLI? Yes, absolutely. We still need to know the Cisco CLI. And if you go to the subreddit, you know, r/networking or r/CCNA, you're going to find that there are a number of sysadmin network admins out there that have, you know, definitely found many instances where they couldn't manage a problem adequately using whatever control plane or control interface, management interface they were using. They had to go into the specific router or switch through the CLI management interface to make adjustments. So our three core components of the ACI architecture. So we've got our application network profile, and that's our end groups and connections. So here, let's get a whole bunch of new acronyms to play with. Our APIC, our application policy infrastructure controller, so Cisco APIC EM is enterprise management. And the APIC is positioned between the APN and the ACI enabled network infrastructure. The APIC translates the application requirements into a network configuration to meet whatever needs are necessary. And our Cisco Nexus 9000 series switches provide application aware fabric. And here we're really talking about fabric for our media, kind of, sort of, because it's the generic commonly used term would be fabric. So here we've got our core components. We've got our customer contract. We've got our VLANs. We've got our VMware, right? Because we need that hardware abstraction layer. That is what all this is hosted on. We may have web services, application, database. So all those things are going to be managed through the ACI, through APIC. So with our controllers, we've got a spine leaf topology. So the leaf switches attach to the spines, but they're never attached to each other. So similarly, normally you would have your switches connected to each other, right? So we don't have them connected to each other now. They are not connected to each other. They are connected only, the spine switches only attached to the leaf and the core switches. So here with this topology, everything is one hop from everything else. When compared to SDN, the APIC controller does not manipulate the data paths directly. Instead, it's going to centralize the policy definitions and the programs, the leaf switches, to forward traffic based on whatever defined policies are set. So this is just creating a whole new scalable infrastructure, or I don't even want to call it infrastructure. It's more like an outfrastructure, you know, of your network. So the Cisco APIC, Cisco Application Policy Infrastructure Controller Enterprise Module, so APIC EM, is going to extend the ACI aimed at enterprise and campus deployments. And to better understand it, it's better to take a broader look at the three different types of SDN. So here we have a device-based SDN. We have an application and the data plane. And here we have a controller-based SDN. And as you can see here, the applications can interface with the controller responsible for managing devices and manipulating the traffic flows throughout the network. Cisco Open Controller is a commercial distribution of Open Daylight. So there's our Cisco commercial. And then we have policy-based SDNs. So as you can see here, policy-based SDNs include a traditional policy layer that operates at a higher level of abstraction. So it includes built-in applications that automate advanced configuration tasks via a guided workflow and a user-friendly GUI. No programming skills are required, and Cisco APIC EM is an example of this type of SDN. So here is a screenshot of Cisco APIC EM. And here we can see our network, we can see our nodes, we can see our topology. So it's sort of like a packet tracer on steroids, because we can really see everything going on. We can manage everything really easily. We can do, if we go down the list of, in the menu bar there, we can see discovery, which is where it can send out pings and discover and access devices and host inventories. Our host inventory, we'll take a look at everything that's on our system. We've got the topology view showing here. So we can trace a path between endpoints, and we can also set policies. So our APIC EM path trace, so that tool looks at specific ACLs on the path between two end nodes, and it displays any potential issues. So how many of us have had problems, configuring our ACLs and trying to figure out, okay, well, which interface do we put this on? Is it incoming or outgoing? Where do we put it? So this is going to take a look at that and analyze it. You can see where any ACLs along the path are either permitted or denied your traffic. As you can see here, notice how branch router 2 is permit all traffic. The network administrator can now make adjustments if necessary to better filter the traffic. So this sort of takes some of the pain out of our ACL lists, which is nice, right? Being able to see exactly what's going on. So one of the labs was to install Linux on a virtual machine and explore the GUI. We're not going to do that because you don't all have the resources available to you to do that. But it's a good idea that you make sure that you install Linux on a virtual machine. Inevitably, at one point or another, you will be doing that, most likely in CSCI55 or in CSCI49 or in CSCI26 perhaps. Or you can just do it on your own. Don't forget, if you're running Windows 10, in order to enable Hyper-V, you need to go into the Windows components in your applications properties and enable that component. So there's a whole new world out there of SDN and cloud resources and cloud computing, and it's going to be your job to get comfortable with it and to manage it. And there's some benefits, as far as management goes. It makes it much easier for us to manage something given a GUI interface with a browser-based setup. Way easier than terming into each different router and switch. The three main cloud computing services, make sure that you're familiar with those definitions by NIST. We've got software as a server, platform as a service, and infrastructure as a service. We've got our 4 different types of cloud computing: public, private, hybrid, and community. Virtualization, of course, is the foundation of all of your cloud computing. And we've got type 1 and type 2 hypervisors. The type 1 hypervisors, it's bare metal. It's installed directly on the server or networking hardware. Um, and when I say directly on the server, I'm talking about the physical hardware appliance. Type 2 hypervisor is a software application that creates and runs VM instances layered on top of the operating system itself. So there really is a lot to go over. Traffic flows in the data center differ way different than the traditional client server model. A data center is going to have more traffic being exchanged between virtual servers, so our east-west traffic, and less traffic going to and from the internet, north-south traffic. Our major network architectures that have been developed to support this is SDN, our software-defined networking, and ACI, our Cisco application-centric infrastructure. And components of SDN that run the gamut through all of the vendors would be OpenFlow, OpenStack, and some other components. But we've got those protocols so that we can manage all of our devices equally well. So we've got, so this talked about Cisco APIC EM, right? Well, there's also Cisco DNA. So they're similar and they're different. And we'll talk a little bit more about that next chapter. But our Cisco ACI is behind all of that. And so our APIC EM and SDN and DNA are going to be using that. ACI is more innovative than our regular old SDN approaches, because this is a rapidly growing technology. It's going to be ever changing, so you're going to have to stay apprised of all of the latest tools and things going on. So we've got our 3 different types of SDNs. We've got device-based, controller-based, and policy-based. And we've got Cisco APIC EM, which is policy-based. And it's going to give us a single interface for our entire enterprise network management interface, which is just lovely, because then we can view the topology, we can trace our paths between points, we can set policies, we can see whether or not our ACLs are working properly. So that path trace tool is absolutely wonderful. Okay.